In chapter 3, we start off talking about the different types of forces that we can experience on Earth. After that, we have a discussion between what is mass and weight, and you gotta distinguish between these two things. It's quite a long discussion. After the discussion, then we talk about resultant force in terms of Newton's first, second, and actually later on third law. Then we need to be able to draw these things out in a free body diagram and also using the um, graphical method, similar to our vector drawings before. You need to solve questions concerning this resultant force, talk about inertia, which is similar to first law, and finally, we're going to talk about something we talked about in kinematics, which is what happens when something falls, but now we have to consider air resistance, right? So that's how this whole chapter is generally shaped. A lot of links to what we talked about in the previous chapter too. Let's start with the first one. Let's do the easy one. Just talking about contact and non-contact forces. So you need to be able to understand that these are contact forces and these are non-contact forces. Now, from the entire list, the things that we want to consider most in this chapter would be gravitational force, air resistance tension, normal force, frictional force, right? The rest of them do come about in other chapters, but we want to be able to be very clear about these 1, 2, 3, 4, 5 things, right? These over here would come about especially when it comes to drawing your free body diagrams later. Now, let's zoom a bit more into each part. Frictional force, some basic concepts must remember, right? When you have friction, all you need to know is that friction is always going to be going against or opposite the direction of your motion. That is to say, if I have a box that's moving forward this way, friction is going to be found in between the surfaces and be acting in the opposite direction, right? I'm not talking about whether the force is equal or not. That's not the discussion here. But talk about the fact it's going to be in the opposite direction to my motion. What does normal force mean? Normal has the idea of direction, not in terms of whether it's common. We've actually seen the idea of normal in Sec 2 when you looked at a reflection, when you have an incident ray and your reflected ray. And then after that, you have this very interesting thing over here known as the normal. That's 90 degrees to the surface. So the idea of normal force is that what is that force that is occurring 90 degrees from the surface when you press on it. So the idea would be if I have an object here, okay, let me just draw over the same thing. If I have an object here, and I know that I'm pressing down the object over here like this, correct? Now the surface is going to be acting on that same object and pressing in the opposite direction, 90 degrees to the surface, and be pressing this way. Okay, this is especially important when you're talking about Newton's third law. So normal in terms of direction. Air resistance over here, at the bottom here, let's look at air resistance. One important physics fundamental to understand is that air resistance increases as my velocity increases. It's that same idea as like friction, and it's going the opposite direction, but more than that, it actually becomes greater as you speed up. So this is a very important concept as we talk about when people are free falling through the sky, and when the person is falling this way, when you're going very slow, there's very little bit of air resistance on you. But as you get faster and faster and faster, then air resistance actually increases. Tension is quite important when you think about what happens in a string or in a rope as you hold up something. So if you imagine that there's a picture over here that's being hung on a string, on a nail right here, what is the force inside the string? Now we know that the weight is going to pull it downwards, but inside the string, you're going to have this tension that pulls upwards in this direction, right? So it's opposite to the direction of pull. Tension pulls it in the opposite direction. So as we look at all of these, there's the idea of these opposite things, right? Frictional, normal, air resistance, tension. Seems to go opposite to the direction in which a force is being applied on it. Now, for non-contact forces, we look at gravitational force. This comes down to our first discussion, which is about mass, and we're going to look at how it's different from weight. So when we talk about gravitational force, we're talking about what is that pull on a mass whenever it enters a gravitational field. Ooh, that means now we need to talk about mass and weight. So we need to define what is mass. Mass is the amount of substance or matter in a body. Now, we did talk about mass in chapter 1, and we did say that when I measure mass, I'm going to be using the SI unit kg. That's for mass. So if I were to put a mass on the Earth, you know very well that because of gravity, there's going to be a pull towards the center of the Earth, correct? That's gravitational force. Now, what does gravitational force really depend on? Well, two things. It's going to depend on how big this mass is, but it also depends on the gravitational field strength of what's pulling it in the first place. That's quite a few words. So let's break it down a little bit more to be clear. So the gravitational force is the pull, isn't it? Now, gravitational force can also be said to be my weight, right? So another word that we can use technically for gravitational force is the weight. Now, what else actually affects this gravitational force would be the gravitational field strength. Now, to talk about the strength of the gravitational field, we need to talk about what's a gravitational field. A gravitational field is a space, a region in which a mass like this is actually going to be experiencing a force due to that gravitational attraction. So gravitational field, imagine it's that area around you, correct? So depending on that field, whether that field is a very strong field or weak field, I'm going to be experiencing a different type of force. So then what is the gravitational field strength? Simply put, it's how much gravitational force each mass would experience at that position. Now, it may make a bit more sense if you put some numbers into it. We know that on Earth, the gravitational field strength, otherwise known as G, is equals to 10 Newton per kg, which means for every one mass, for 1 kg, there's a pull of 10 newtons. So that means, right, when it comes to this object over here, what is the gravitational field strength for Earth? Every kg, 10 newtons, correct? So that gives us the idea, wait a minute, if that's the case, then I should be able to figure out what is my weight. And that is where we get this formula, W equals to M times G. W is weight, M is mass, G is gravitational field strength. So if my mass on Earth over here, let's say is 3 kg, that's my mass, what is the weight on Earth? In this case, it would be 3 multiplied by 10, gravitational field strength, this would be 30 newtons. Hey, there you go. Weight is a force, and the SI unit for force is Newton. Now, we did say that it depends on the gravitational field strength, and gravitational field strength differs from planet to planet. The smaller things, the smaller celestial bodies, let's say like the moon, okay, which is smaller. If I had this same object on the moon, it was going to have a smaller gravitational force, right? The weight is going to be less, but the mass is still the same. It's still the same amount of substance, but on the moon, it's going to be much less. What has changed would be the G. The G would be less, and since the G is less, what happens on the moon? My weight will be less. Here's the thing though, if I were to give you and tell you that the G of the moon, so I'm just going to subscript moon, G on the moon is 1.6 Newton per kg. That is to say, right, for every kg on the moon pulls 1.6 newtons only, which is to say, the weight on the moon, using the same formula, m times g, the mass didn't change, it's still 3 kg, but the gravitational field strength is now 1.6, and that gives us a very different weight. Same mass, different weight, different gravitational force experience on this celestial body, on the Earth, on the moon. All good? This is actually a big part. Most of the time, the questions they will ask you is they'll give you certain things. They'll either give you the mass or they give you the weight. You might be asked to calculate the weight. That's just W equals mg, right? Sometimes G is given, sometimes G isn't. But if it is on Earth, you just remember that G is going to be 10 Newton per kg. Wait a minute. Why does this look so familiar? Why does this look like something we've done before? In the previous chapter, we talked about acceleration due to gravity. Yeah, we did. And we also realized that acceleration due to gravity, right, A is equals to 10 meters per second squared. That's very odd. It seems to work out in the same way. Later on, when we have the formula F equals to ma, you realize that, whoa, wait a minute, they seem very, very similar, right? So something to note, G will be 10 Newton per kg, or G can also be 10 meters per second square if we talk about acceleration due to gravity. The final thing to note is that I can't use the same instruments to measure mass and weight. Now, weight is going to depend on how much is being pulled over here, correct? So when I want to measure weight, what I'm going to be using is that I will use a spring balance, right? A spring balance is what I use to measure weight. But when it comes to measuring mass, I don't use a spring balance, I use a beam balance, or I can also use an electronic balance, which is calibrated very much like a beam balance. See, for weight, it requires a pull, and that's where the spring comes in, right? It's going to pull differently on the moon compared to the Earth because of the gravitational field strength. But when it comes to mass, I need to compare one mass to another to see if they're equal. That's where I get my beam balance or electronic balance. This is linked to the next chapter concerning moments, where you have the seesaw idea, right? So with that, I think we have covered the general differences between mass and weight. The rest can be found in the textbook. Now we move on to Newton's laws. So the next bulk of this chapter talks about the idea of resultant force, balance, unbalanced forces. We always talk about balance, unbalanced, yes, but please remember the key word we're looking for isn't about balance, unbalanced forces. We are looking for this wonderful word known as resultant force. Okay, resultant force must be the key idea you bring across in this chapter. When we say resultant force, we're really just saying what is the overall force acting on an object. So let's go with balance and unbalanced forces. Okay, let's shift it a bit more here. Let's look at two objects over here. One object here, one object there. Balanced forces would be something whereby I have two forces acting on it, and these two forces are equal. 5 newtons, 5 newtons, right? As compared to this one up here, let's say this is 5 newtons, and this is, let's say, 12 newtons, right? It could even be, in this case, one whereby I just have 7 newtons over here, right? That's also unbalanced, right? In this case over here, what's the result of this object being pulled in opposite directions with the same magnitude of force? Is there any resultant force? Well, no, right? What about this one over here? What's the result of being pulled 5 and 12 in these directions? Well, the result is 7 newtons in this direction. Oh, similar to this, right? So what you do get is you have a resultant force in these cases, and there's no resultant force in this case. So the first question is, what's the resultant force? So on the left side, balanced forces will say I have a 0 resultant force, and on the unbalanced side, in this specific case, I see, oh, I have a resultant force and it's 7 newtons, and it's to the right, because it's a scalar, a vector, so there's a direction. Now, basic question that we have learned before lower secondary, we know that a force is a push or pull, and when we apply a force on an object, right, it could do a few things. If let's say we hit it here, it could change my direction, right? It could change my speed. What else could it change? Generally, it changes the state of motion. It could be not moving. Then when there's a force acting on it, resultant force acting on it, ooh, it starts moving in a certain direction. It could speed up. It could even be one where I am trying to slow down the ball, right? So the ball's moving very fast, and then I apply a force here, and then in the end, the result, it slows down or it stops, right? So it changes state of motion. So the question would be this: what then will be the state of motion when there is 0 resultant force or when there is a resultant force? So in the case of balanced forces, there are two possible states of motion. One, I could be at rest, right? This actually happens especially when, they just say especially twice, when you have, let's say, let's look at this same object up here. Okay, fine. Let's say this box over here. It's not moving, originally it's not moving, right? It's at rest. And then I apply a force both here, 5 newtons, and another force here, 5 newtons. Let's assume that it doesn't crumble, it doesn't deform. I apply it at the same time, boom! Does it move? No. There is no resultant force. It remains in state of, of motion, of being at rest. Now imagine that I have a ball, okay, and this ball is actually moving at, let's say, 2 meters per second, constant speed, okay. Now I have a jet. I have something to blow air, and I blow air both here, and I push it with this jet of air at 5 newtons, right? But at the same time, I also use another um, air blower and blow also 5 newtons here, correct? Now, the question is this, so let's focus here. This is already moving at constant speed, right? And apply these two forces over here. Is there a resultant force between these two 5 Newton forces? The answer is no. So will it slow down? No, it won't, because there isn't any resultant force, right? Neither will it speed up. It's as good as nothing really happened to it. So it continues on its way at constant speed. Now, how would it slow down? It will only slow down if, let's say, this wasn't 5 newtons, but instead this was, let's say, 6 newtons. Now, if you said that one is 5, one is 6, the resultant force would be one whereby on this ball there's a resultant force of 1 newton in that direction, and this is opposite to the state of motion, correct? So if I'm going to apply a 1 newton force the other way, that has to mean that I'm going to then see it accelerate in this direction. Ooh, isn't that opposite to this? There will be negative acceleration. That means it's going to decelerate. This will then slow down. If it was the original 5 and 5, it's not going to speed up. It's not going to slow down. It's going to continue on like nothing happened because no resultant force. Right, let's get back here. So it could be at rest, or it could be continuing at constant speed. Like in this case over here, it just continues at constant speed. Now, these two possibilities are the number one things you look out for in the question, because it actually tells you what is happening to my object. See, the moment you say that my object is moving at constant speed, it tells you that this is a case of balanced forces where I might have two forces, and the two forces acting on the object are going to be equal, right? Most importantly, you're going to say that, hey, in that case, resultant force is 0. Now, what is so important about this state of motion and resultant force is because when you talk about Newton's second law, we look at this thing called F equals to ma. F over here stands for resultant force, not just force, but resultant force. M stands for mass, A stands for acceleration. Okay? Now, that means that if I do have a resultant force, it tells me that an object with a certain mass is going to be accelerating in that direction of that resultant force. If I have resultant force, I will have an acceleration, right? So in this case, what's the state of motion if I have a resultant force over here? In this case, 7 newtons. It's going to tell me that, hey, I'm going to be moving at constant acceleration. And this acceleration I can actually calculate. So let's say, for example, that this object over here is actually 2 kg. So my question is this, what is the acceleration of that object when it has 7 newtons of resultant force? So let's find out. F equals to ma. Let's shift this a little bit. I know that my resultant force in this case, right, either this state or this state, both are the same, right? I have a resultant force of 7 newtons. 7. My mass is 2. I do not know my acceleration. Acceleration therefore will be 7 divided by 2. That gives you an answer of 3.5 meters per second square. That's constant acceleration. We need to use this situation to look at most of the questions we have from this chapter. right? It comes down to basically these two cases. Remember, you're thinking about resultant force. Wow, did we talk about Newton's laws already? Yes. This is concerning Newton's first law, which is an object at rest stays at rest, an object in motion remains in motion unless acted upon by an external net or resultant force. And over here, that's Newton's second law, which is resultant force is a product of the mass and acceleration of the object, right? F equals to ma. Fantastic. Now you can tell so far we've been drawing a lot of these things over here, correct? What are these things? These are known as free body diagrams. Free body diagrams are one of the most important things that you must learn how to draw when it comes to solving questions involving dynamics, right? So let's say this is my question. So here we have a very typical question. Let's underline some important things. It tells me I'm pushing this box at 20 newtons. Now this does not mean this is my resultant force. All I know is that it's being pushed at 20 newtons. So let's draw that out first. Okay, I have box. Okay, clearly it's on the floor, right? And I'm pushing it 20 newtons. So let's push it here. Let's put 20 newtons. Right, next thing I see is that it's moving at a constant speed of 6 meters per second. Ooh. Wait, which thing is more important? The fact that I said constant speed or 6 meters per second? The answer is here. The fact that I said constant speed. That is to tell me that I'm looking at a situation where I have balance forces or resultant force is 0. So now that tells me that I'm going to be looking at friction going in the opposite direction, correct? So friction is going to be over here between the surfaces, and I know because constant speed, right? That tells me 0 resultant force, right? So since it's 0 resultant force, it must mean that if I'm being pushed 20 here, then this over here, the friction, has also to be 20 newtons, right? Usually this type of question would be state the force of friction because it's very, very straightforward. Now let's try to do a different question where we are not looking at balanced force situation, but we're looking at unbalanced force situation. Okay, let me shoot this a little bit up higher. So now this is a bit different, right? This one tells you there's moving a constant acceleration and it gives you the mass. Ooh, wait a minute. How does that work? So let's underline once again. So this is the force that is being pushed. I know that it's constant acceleration and this acceleration is 6 meters per second and the mass is this. So I'm going to start annotating it. I know that this 3 kg would be my mass. I know that the 6 meters per second is my acceleration. And question, is this resultant force? The answer is no. It just tells me one of the forces that I'm pushing my box, correct? It just tells me that I'm pushing with 20 newtons. It does not mean it's my resultant force. How do we find resultant force? We use F equals to ma. This m, this a. So let's find out what's the resultant force. Resultant force is equals to mass times acceleration, which is 3 times 6, 18 newtons. Hey. So what is actually happening is that I know that the resultant force is 18 and it's going to be positive 18, right? It's going to be in this direction. So 20 and another force is going to give me 18. Is this force adding to it or is it going to be subtracting from it? I think you can tell that this resultant force is equals to my push, right? And you have to go to minus the friction, correct? Now we know that this F is equals to 20, which is what I have over here, minus my friction. So let's rearrange it. I'm looking for what is the frictional force, and that's going to be equals to 20 minus F. This is basic mathematics, it shouldn't be too difficult. 20 minus 18 equals to 2 newtons. That means friction is going to be acting 2 newtons this way. And does it work out? Yeah, it does. I'm going to write it this way, that my resultant force is 18 newtons, like that. How else could you annotate this? Maybe before you started, you could have written that it is going over here. It is going at 6 meters per second square, and then this is 3 kg. This is other ways that you can annotate it, right? So this is how the questions can differ between one which is balanced and one which is unbalanced forces. Now, we still seem to be on the part where we are drawing all of our things, right? These free body diagrams. A free body diagram is basically one where you're drawing all the forces acting on an object. So far, everything you've seen is that, see, on this object, these are the forces acting on me, these are the forces acting on me, these are the forces acting on this. Draw all the things which are acting on that object, right? It is very important to talk about that because maybe I can talk about um, this part first, right? Since I'm talking about free body diagram. Um, you see, when we remember the different forces acting on me, we remember there's something called air resistance, correct? Now, if you're falling, like we saw in this diagram over here, you're going to have two forces acting on you. The first force, of course, would be my gravitational force, which is downwards. But as you continue falling, you have air resistance as well, correct? So let's go to that part. Talking about describing motion of bodies with a constant mass falling in uniform gravitational field with or without air resistance. This requires us to talk about terminal velocity. So since we're on the point of drawing our free body diagrams, let's do that part first. Okay, so if I have an object, right, and I just start to let go of the object, you know that the moment your hand releases it, it's not going to move yet. It's going to start to accelerate, but initially it only has one force acting on it, and that is going to be my weight. It's not moving fast, it's not even moving at all. It's going to accelerate in the next moment. So because it is not moving fast, will I have any air resistance on it yet? Well, no. It only increases as my speed increases in opposite direction. So this is at first, right? At first as it starts to drop. So let's show you where it is. So maybe you have a zoomed out part over here. This is the ball, and this is my hand holding on to it, right? What an ugly hand. I use your imagination. Okay, so this is the first part over here. Okay, where I just have to, it's so ugly. Oh boy. Okay, so I just have to let go, it's not moving yet. So what I do have is that my resultant force is going to be, my resultant force is just going to be equals to W, right? Which is my weight. That's my resultant force. And it's going to be moving at 10 meters per second square. Correct? That's my acceleration, isn't it? Now, what happens when it starts to fall somewhere here? Okay, that means it has fallen from my hand, now it's going here, it's dropping. Okay, now how will I draw that? Right, at stage 2, does my weight change? Well, it doesn't, it's still the same mass, so the weight didn't change. It's still the same gravitational field strength, so it's still the same weight. But what has changed is that I'm going to start to have a bit more air resistance up this way, right? Air resistance. Let's put A small r, air resistance. So you do realize that, hey, wait a minute, my resultant force isn't the same. My resultant force is actually becoming smaller, right? F is equals to W minus AR, right? Of course, we can see clearly, right, that the weight is still much bigger than air resistance, right? Still much bigger, as you can see in the drawing over here. So what would my acceleration be? My acceleration would clearly be less than 10 meters per second squared because my resultant force has changed. I'm going to be having a smaller um, acceleration, right? See that? My F got smaller already, right? So if you remember F equals ma, if I have a smaller force, my mass is the same. If this force is smaller, my acceleration is be less. Now, what happens when it comes to a point where it has fallen so far, so much so that it increased speed? Now, remember, it's still accelerating. It's accelerating less, but it's still accelerating. So what happens is that it gets faster and faster and faster, even though the change in that speed is getting smaller. I speed up, and I keep speeding up until that air resistance becomes exactly equal to my weight. So what then happens when W is equals to air resistance? When you look at F equals to W equals to W equals, I'm so sleepy. W equals W minus air resistance. Since these two are the same, I'm going to have a case where my resultant force is equals to 0. There's no resultant force. So what have you learned about no resultant force? If there's no resultant force, well, it can't possibly be at rest in this case, right? It's falling through the sky. So it's going to be a case where I'm at constant speed. This is similar to the graph of a velocity time graph where this is happening, correct? Now, recall that the gradient of a velocity time graph tells you your acceleration. Now, clearly acceleration has been getting less and less. When resultant force is 0, we also said that there's no acceleration, correct? Acceleration is 0, which means my gradient was 10, then gets less until my gradient comes 0, which is the case, right? A gradient of 10, and then over here, it's flat, 0 gradient. I have got really, really fast, but here's the thing. At this point over here, and if I were to draw it more carefully, let me try to draw the ruler. Does it work? Yeah, something like that, right? At this point, speed is constant already, and this is the highest possible speed you can go. This is known as terminal velocity. So what's terminal velocity? Terminal velocity is that maximum speed of an object, right? You reach when the forces acting on the object are balanced, right? So what is balancing? The weight. The weight is balanced by the air resistance. Okay, so you have a free falling object, and then I reached terminal velocity because resultant force becomes 0. The weight is equal to air resistance. There we go. So that's terminal velocity. So far, we've talked about Newton's first law, second law, but we have not really talked about Newton's third law. This is about action-reaction pairs on two interacting bodies. Two bodies. So far, everything we're drawing seems to be on just one body. So this is where Newton's third law comes into play. Let's say I have a floor ball hitting this stick, okay? So let's call this the stick, and let's call this the ball, right? Now, when I do hit the ball of the stick, right, I have a force by the stick on the ball, correct? Now, just as much as when you smack something, right, your hand gets very painful, it's because the object which you're smacking, right, really acts on your hand and hurts you back. It's kind of like saying that when the hand hits the face also hits the hand, because the force by hand on the face will be equal to the force by face on the hand. You recognize that we're looking at two different objects, correct? And these two objects are interacting with each other. And we're going to be using the idea of BO. The way that we talk about this is always by, on, by, on. So in the face case, right, over here, we can say that the force by hand on face, which is when you go piak on a person's face, right, will be equals to the force by the face on the hand, which is really why your hand hurts after that, right? Because the face has hit you back. Now, it's also going opposite directions, right? So if you think about it, right, on face, So on face, right? Force by hand on face will be this direction, isn't it? Yep. And this is on my face. But the other one would be force by face on hand, and you go this way. Ooh, isn't it? This blue is a force by the face on the hand. Ooh, this one. This over here is a force by the hand on the face. This one. Now, this wouldn't be mathematically correct because we do see that they're in opposite directions, correct? For that reason, I'll put it like that, that they're going in opposite direction. Remember, the minus doesn't tell you about value, it tells you about direction. So let's try for this one over here. What would it be? The force that the stick hits the ball. So force by stick on the ball. Well, the stick will also receive a force, isn't it? Will be equal to the force by the ball on the stick. Right? So this is Newton's third law, which basically is I'm saying that I would have to have a pair. What is this pair? I have a action, reaction pair. Now, how do I identify action-reaction pairs? In an action-reaction pair, the forces will be equal, right? See, equal, right? It's not more or less, it's equal, right? If I hit the face softer, my hand doesn't hurt as much because the face doesn't hit my hand as hard, right? So I'm going to see that for this action-reaction pair, right, I'm going to have equal magnitude. Other than equal magnitude, I'm going to see that they're going to be opposite in direction. Correct? And the last important thing that we realize is that when I look at this action-reaction pair, they're acting on two mutually opposite objects. What does that mean? Let's write it down. Two mutually opposite objects. See, mutually because these are the two things which are interacting, right? So we have this mutual force over here, right? Opposite because it's this opposite to that. So I'll see two different objects. I won't see one object, I won't see three, I will only see two. So if you look at the general formula that's given, usually what is written is this: F A B is equals to negative F B A. So let's try read it out. Force by A on B will be equals to force by B on A. Equal magnitude, opposite direction, and is acting between two mutually opposite objects, AB, BA. Do I see a C inside? No, I don't. And it's important that we discuss it here because we just looked at this. And the question is over here when I see this: is this an example of an action-reaction pair? The answer is no. How is that so? Well, let's think about it, okay? So let's now figure out what exactly is weight and air resistance, okay? So let me now draw weight. So let's explain weight in terms of force by something on something. When you think of weight, basically weight is the force by Earth on that object, right? Makes sense, correct? Because the Earth need to pull on that object. It comes from the Earth, by Earth, on object. What about air resistance? Air resistance is basically, right, the force acting by air on that object. So I have FAO, I have FEO. And let's see whether this actually satisfies our three conditions of magnitude, direction, and two mutually opposite objects. I think it's quite clear to see that the forces are equal, the opposite direction, but here's the problem. How many objects are we looking at here? We're looking at a total of three bodies: air, earth, and the object, right? That is not two mutually opposite objects, that's three. For that reason, this isn't an action-reaction pair. So is this an example of action-reaction pair? No. One of the easier way to see is actually, hey, wait a minute, all these objects, all these forces are being drawn on that one object. Free body diagram, right? Everything on that object. It must be two mutually opposite objects. So then from this diagram, could I find two other acceleration pairs? Well, yes, I can. How does that work? If I were to look at air resistance is basically force by air on object. So if you use the idea of FAB equals FBA, it just tells me that the action neutron pair, the other one would be force by object on the air. Likewise for this, if weight is force by Earth on object, it means that the action neutron pair, the corresponding pair would be force by object on the Earth. Yes, you do actually exert a small amount of gravitational force on the Earth, and that amount is actually the same as your weight. But it's just that Earth doesn't pull back towards you in a way which is observable because the Earth is so much bigger compared to you. So these are action-reaction pairs. These are action-reaction pairs. Your weight and air resistance is not an action-reaction pair. Now, the second last thing that we need to consider would be the concept of inertia. If I'm not wrong, another video has been done concerning how do you draw this in the graphical method. So the last thing I'll consider right here would be about inertia. Now, it is still the discussion of mass. So it looks like we've actually gone one big round. We're back to the idea of what is mass. So when I talk about mass, mass has a special property known as inertia, and inertia is defined as the resistance or reluctance to change the state of motion. Now, we have talked about states of motion. I could be at rest, I could be moving at constant speed, right? So let's use two examples. Let's look at two objects rolling down a hill, one with a much bigger mass and one with a tiny mass. Maybe it's just a pebble. Now, this huge boulder, if it's, let's say it's rolling down at a constant speed, let's say both are moving at 10 meters per second, right? Now, the consideration now is about the mass and its reluctance to change its state of motion. This giant boulder is going to be very hard to stop. This one is relatively easy because its inertia is less. This one is going to take so much effort to change that state of motion, right? That's inertia. Likewise, if these two rocks were staying still, well, you can tell this is going to be really hard to start moving, right? Because it doesn't want to resist, it doesn't want to change the state of motion, which is at rest. But this tiny one, because its mass is so much smaller, it's much easier to overcome its state of motion, which is at rest. Easy to move this, easy to stop. Hard to start moving, hard to stop. That's about inertia. All right, we're done.